Newton's law of universal gravitation. I want to start with that. The law looks like this. And I'm leaving out some bits of it on purpose because the bits I'm leaving out have to do with direction and vectors and stuff. So I'm going to leave that out for today. We will come back to it later. But what it says is that if you have any two objects in space, any two at all, so object number one and object number two, they will experience a force of attraction. That's important because I reminded you that most of the fundamental forces are attractive forces except for the electrostatic force. So they will experience a force of attraction. That force of attraction will lie along the line connecting them. So if I connect their centers, there will be a force on planet 2 from planet 1, or object 2 from object 1, and there will be a force on object 1 from object 2. These forces are equal and opposite. They represent a Newton's third law pair. The size of that force will depend on the mass of object 1, the mass of object 2, and their center-to-center separation distance. Now, this is known as an inverse square function, and it's one that you need to become acquainted with because it shows up quite a bit in science. Inverse square functions decay rapidly as the separation distance increases. So if we want to consider what the force of gravity kind of looks like, it's very strong when things are close, but decays rapidly as you get farther and further apart. Now, the force of gravity exists between any two objects with mass, but it only can deal with two objects at a time. So if you have a third object floating around out here in space, well, that third object has to be dealt with separately, meaning you have to pair all the objects up and find the forces on them separately. So there's a set of forces acting between these two objects, and that would be its own force equation. Right? The force equation itself only deals with two objects at a time. Quite famously, the two-body problem is well handled with our basic arithmetic. The three-body problem is almost impossible to solve. And that's why there's books about the three-body problem. And I'm not talking about the glorified story that's on Netflix or whatever. The three-body problem is actually a very challenging problem to solve if you're trying to deal with orbital dynamics. So dealing with three bodies that all are influencing each other makes for a very complicated scenario. But two objects, not so bad. But part of it has to do with the fact that the Newton's law of universal gravitation and all laws that deal with gravity only deal with two objects at a time. Now, I'm going to get this out of there because I don't need it. I want you to consider this for just a moment because I'm saying something that feels a little bit like false advertising. For example, all of you have mass. You're not feeling compelled to be pulled towards other things in the room that have mass. So why is it that I should believe that this force exists? Part of the problem has to do with this number right here, G. This is known as the universal gravitational constant, capital G. It's important that you recognize that. Remember, I banned the use of that letter earlier in the year because it has been reserved for use here. The universal gravitational constant takes something that's in mass and something that's in displacement or distance and gives you something that's in newtons. That's what this constant does. So it's taking the masses and the masses and the separation distance and giving you a value that's in force. So the gravitation constant's different depending on the units you're using. So if you're using units that aren't kilograms and meters squared, you would use a different value for the gravitational constant. The one thing that matters, though, is we believe that the gravitational constant is the same everywhere in the universe. So if we're trying to calculate the way things behave someplace else in the universe, we believe solidly that this value will be the same no matter where you are. And you're going to love this because it's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And it brings me great happiness to know that you guys are going to be doing your homework tonight and have to write 6, 7 lots and lots of times. I know you're going to say it in your head just like that too. So I'm happy about that. It's the first time that this number might actually stick in your head for a while. But look closely at it. 10 to the negative 11th. So, I mean, let's say that you have a mass of 60 and your buddy has a mass of 70, and you guys are, say, I don't know, 3 meters apart. Now, why don't you feel the force of attraction, no matter how attractive you are to them? Why don't you feel that? Because you have to scale the whole thing by 6.67 times 10 to the negative 11th. That's why. No matter what, no matter how close you guys get, this force is tiny. It takes something astronomically big to create enough force for you to measure. Now, a couple of things about this. Newton had his hands in all sorts of stuff in physics. But this one is kind of magical because he kind of just pulled it out of his head. There's a whole story about, the apple falling and hitting him in a tree. There's no reason to believe that's anything more than just hyperbole. He did teach in a university where there were apple groves, and he did often go out there to think and to contemplate the universe. But there are several laws that predate this that are inverse square laws that also have a similar function. The real magic is how they measure G. That one's the real magic. And I say that because how would you go about doing it empirically? How would you create an experiment that could measure that value? You'd have to have something big enough to generate a force, right? If you're trying to measure a variable which you don't know the value, and you want to do it empirically, you would have to measure all the other values, right? So you'd have to measure a separation distance, you have to measure the masses of objects, and you'd have to measure the subsequent force. The experiment that did it is actually pretty crazy because it was done hundreds of years ago, and it was by a guy named Cavendish. And this part's not that important. I would rather you pay attention than try desperately to write all this down. I like it because it was an ingenious take on it, and it was simple. And he did it in like a barn or a warehouse. He took 2 very large, very massive spheres and welded them together with a steel pipe between them. So it looked kind of like a dumbbell like this. He then hung the whole thing from the ceiling of the warehouse using a steel cable. That part's important because when he set it all up and attached it to the steel cable, the steel cable would eventually come to its rest position, which probably wasn't the way he set it up. Have you ever been on one of those, a swing, and done the twisty of the swing, and you twist back, because it has a kind of a rest position? Well, you can do that with just one chain. It's called a torsion constant, how much it will twist and then come back to its original shape. It's kind of like another version of Hooke's law for things that twist. So he measured the torsion value of the cable. He then took 2 other spheres that he mounted on a rolling platform and placed them in the room, but at the time he placed them far away, measured all those masses. Now this part's where it gets pretty ingenious because he knew the force would be very small, even if the spheres were very massive. So he put a mirror right at the center here, and there weren't lasers back then or even flashlights, so he did it in a darkened warehouse and then cut a small slit in the light of the window on one of the walls so that a ray of light would come in and bounce off of the mirror and project onto the wall on the other side of the warehouse. So then he moved the rolling spheres into position. And when he did so, these would twist a small amount. But it'd be very small to measure how much it deflected, so he would watch as the light moved along the wall. Using the geometry of this, he was able to measure how much force there had to be here to cause the cable to torque this amount, and then work the problem backwards to figure out what G was. He did this without computers or calculators, and the value we use today is almost exactly the same as the one he calculated with this experiment. It's pretty amazing as an experiment goes, and a fascinating testament to patience, I would argue. But what's amazing about it is, like I said, we have not added hardly any decimals to this value over the years. It's hard to measure this constant. So you can imagine, you can buy a Cavendish experimental system now. They sell them in laboratories, and you can do this in a classroom. But again, the experiment now, they use different things. They use stuff with a very very well-known amount of tensile strength cable. Again, a couple of heavy spheres, a laser, so you can get a little bit more accuracy on your spot on the wall and how it moves. But you can measure it in the classroom using a similar apparatus to this. What I want you to recognize is that we believe this value is the same everywhere in the universe. That's important because once we had this value, we could monitor what was happening in other places in our solar system and make calculations we couldn't make before. So knowing this value and understanding that we believe it's the same and having evidence that it's the same regardless of where you are in the universe means you can look at the motion of planets and make predictions about the masses of those planets, how big they are, their radius, separation distance. It changed the nature of how astronomy could be done. So I'll do a couple of basic practices here. And here's the first one I want to do. You need to become familiar and capable of making calculations using these big numbers. And that's usually where things break down, is because you guys are not great with the old calculators. So here's what I want to do. Imagine you are standing on the surface of the Earth. One of the things about this function that you have to be careful about is that r is never 0. Right? That would mean that the two objects are overlapping. So if I want you to calculate the force of gravity on you, you're standing on the surface of the Earth. So the separation distance isn't 0. The separation distance will be the radius of the Earth. That's how far apart you are. I don't think we have to worry about adding that extra meter for the middle of you, because the radius of the Earth is 6.37 times 10 to the 6 meters. If you're desperate, go ahead and add 1 to it, because you're 1 meter away from the surface. But I don't think we have to worry about that too much, if you understand my meaning. And I want you to calculate the force of gravity on you from the Earth. To do that, you're going to need, of course, the mass of the Earth. You're going to need the radius of the Earth, but you're going to need the mass of you as well. Now, to get the mass of you, it's pretty easy. Take your weight in pounds and divide by 2.2. That'll give you your mass in kilograms. I'm a big guy, but I'm going to be nice to myself and say I'm only 90 kilograms. I don't think that's true, but I want to be nice to myself today. So we're all going to say, yes, Mr. Shelton, you're looking nice and thin today. Thank you. I try. I do. All right, so you do you, I'm going to do mine, and you calculate the force of gravity between you and the Earth. We're all going to get different numbers, but that's okay. I have a plan. So that's going to be 5.98 times 10 to the 24th for the Earth, 90 for little old me, 6.67 times 10 to the negative 11th for G, and then 6.37, ooh, you go, buddy, times 10 to the 6th squared. Now look, you guys are not great at calculator. Become better. All right, so we've all got our force of gravity. I'll remind you, you've been doing this all semester. The force of gravity is just weight and has been the whole time. So this is also equal to mg if you're on the surface of the Earth. So let's make sure we've done this right. All we have to do is take your number, 884.69 is mine, set that equal to the mass of you times g, and we should be able to see what the acceleration of gravity is using a more empirical method. So I'm going to take my value, divide by 90, And lo and behold, I calculate that the acceleration of gravity on the Earth is 9.83 meters per second squared. And you should all get the exact same value as I. Which brings me to our first, our first, conclusion. If you want to calculate the acceleration of gravity on another planet, well, you start by taking the mass of an object on that planet, recognizing that the mass of the planet, mass of the object, g over the separation distance, which is the radius of the planet, would have to equal the mass of the object times the acceleration of gravity on that planet. That's what we just did. That's where mg comes from. So canceling out the mass of the object, the acceleration of gravity on a planet is equal to mass of planet g over radius of planet squared. That's our first conclusion from knowing what Newton's law of universal gravitation is about. Okay? It's not on the equation sheet, but you should be able to figure it out. Now with that, problems that you guys are terrible at. I'm going to give you a method for doing it because I think you're terrible at it. So a new planet has been discovered. This new planet is 3 times the mass of the Earth, but has twice the radius of the Earth. What is the acceleration of gravity on our new planet? I'll say it again. We discovered a new planet. The new planet has a mass that is 3 times that of the Earth, but a radius that is twice that of Earth. What is the acceleration of gravity on the new planet? And I want you to do it without any of that. You don't need it. The first thing that you need to know is you need to recognize when we're doing a comparison. This is a comparison problem. All you need to know is that the acceleration of gravity on the Earth is 9.8 meters per second squared. Now I want to show you how to do a comparison problem. You guys ready? The acceleration of gravity on the Earth is also the mass of the Earth, g, over the radius of the Earth squared. We just showed that. Now, at the same time, we want to find gravity on our new planet. But our new planet is 3 times the mass of the Earth and 2 times the radius of the Earth. So the first thing we do is we work out what our new acceleration is, or our new value for the force is, using our modified values. Right? We put modifications to our values. Do you guys see that? So step 1, use the formula, but put in your modifications. Step 2, pull the modifications away from the base formula. So I'm going to pull the 3 out. I'm going to square that 2 and pull the 4 out. What I should be left with is the base formula. So step 1, put in your modifications. Step 2, pull the modifications out and recreate the base formula. And then recognize that the base formula was a value you knew already. And substitute. This should give you the acceleration on the new planet. So the first thing I want you to know when you have to use the big numbers and when you don't. Want to practice again? This one's on you. You get it right, okay? A new planet's been discovered that is 2 times the mass of the Earth, but 3 times its radius. What is the acceleration on our new planet? Again, a new planet's been discovered. The new planet is 2 times the mass of the Earth and has 3 times its radius. What is the acceleration of gravity on our new planet? Question, step 1. I'm going to put in the new values. So g on our new planet is going to be 2 times the mass of the Earth and 3 times the radius of the Earth. Put it into the function. Pull the modifications apart from the function. Put the value in for the original function. And that's how you'll get your 2.2 meters per second squared. These are easy. Get these. If you don't like this particular method, I have 2 or 3 others. This is just the one I'm teaching this year. Let's try one more. Got it. Imagine I have 2 objects, object 1 and object 2. They are currently experiencing a force of attraction due to gravity of 50 newtons. If we double the distance between them, what is the new force of attraction? This is a comparison problem. So I'll say it again. I have 2 objects, object 1 and object 2. They're currently experiencing a force of attraction due to gravity of 50 newtons. If I double the distance between them, what is the new force experienced by the objects? I'm going to recognize this is a force of gravity question. I'm going to grab my equation for the force of gravity. I'm going to put in my modification to the variables. M1 wasn't modified, M2 wasn't modified, R was doubled. I'm going to pull my modifications apart from the base function. I'm going to then substitute my value in for my base function. And I get 50 divided by 4, or 12.5 newtons. Do you guys see how this is done? Another one. This is the last one. Let's go back to my same 2 objects. Let's just see if you guys can do this solo. I cut the separation distance in half. What is the new force between them? Show me you can do this one. You cut the separation. So my original situation, M1, M2, G over R squared is 50. Put in my modification. M1 stayed the same, M2 stayed the same, but R was cut in half, so half of R squared. Pull the modifications apart from the base formula. So M1, M2, G over R squared, and I have 1 over 1/4. Plug in for my base formula, which gives me 4 times 50, which is 200 newtons. Again, these aren't physics questions. These are 8th grade ratio problems. All right, I'm going to modify this to make it harder. Let's see if you can do the harder question. What do I have to do to the separation distance to bring the force down to 20 newtons from 50? What do I have to do to the separation distance to bring the force down to 20 newtons from 50 newtons? Can you adapt to a new type of problem? To do this problem, you follow the same step. What are we modifying? The distance. So M1, M2, and G stay the same, but there is a modification to the distance. So put your modification in. This new one equals 20. We know the answer. But the process is the same. Separate the modification and build your base formula again. So I separate my modification, my base formula, M1, M2, G over R squared. Process is still the same. So pull your modification out, build your base formula, and then do substitution. That's it. Solve that for A. So I'll get 2/5 equals 1 over A squared. So A is the square root of 5/2. So you still put the modification in. You still pull the modification out, except this time you know what the answer is going to be. So you put the answer in, but you still do the same substitution. It's the same problem. Work these out. There's a ton of these in your textbook. I put like 2 on your homework. Do the ones that are on the homework. Now for the real thing I want to talk to you about. And I found out something from first period. And if it's true in first period, I know it's true here because you guys tend to be similar. We're talking about orbits for a minute, but to do so, we have to talk about ellipses. An orbit occurs when there's 2 objects experiencing a force of gravity, but one of the objects has enough velocity to avoid falling into the central object. That's really what it amounts to. The moon is falling towards the Earth all the time, and the Earth is falling towards the moon all the time. But the moon has enough velocity so that by the time it makes it to the Earth, it's already moved out of the way. That's what's happening. So an orbit is a delicate balance between gravity and velocity. But to understand orbits and orbital mechanics, you do have to understand a few things about ellipses. So I want to start with elliptical orbits first, and then talk a little bit about how ellipses and circles are similar. I'm going to give you some vocabulary here because I found out, again, in the other class, that you guys don't have this vocabulary. For example, anybody know what this line is called? It's the semi-minor axis. When compared to this one, which is called what? The semi-major. An ellipse has a minor axis and a major axis. It also has 2 focal points located somewhere along the major axis. If you're in pre-calc now, eventually you'll learn how to calculate the location of the foci of an ellipse and a hyperbola and a parabola and all that stuff. But until that time, just assume that they are there. We rate the eccentricity of an ellipse by the ratio of the minor axis to the major axis. The closer that is to 1, the closer this is to a circle. Most orbits are elliptical. And so if we kind of take a look at the Earth, which I'm going to use a red dot here because I don't want the blue dot to be confused with the blue ellipse, because I know some of you think they both were blue. We talked about that yesterday. And I'm going to put the sun here. In an elliptical orbit, the thing being orbited is at one of the focal points. And the thing doing the orbiting is traveling along the elliptical path. I'll say that again. In any orbit, the thing being orbited is at the focus, and the thing doing the orbiting is traveling along the elliptical path. This becomes more confusing when the 2 objects have a size that is close to each other and they have to orbit about their mutual center of mass. That will be a more complicated problem, but that's not too complicated for this class. For right now, we're just going to do some overarching things about elliptical orbits, but then we're going to do mathematical things about circular orbits. So here's the things I want you to know about elliptical orbits, and I think these things are obvious. When the planet is close to the star, and I'm going to say planet and star, but you understand this also works for satellite and planet. Doesn't really matter. Any 2 things in orbit will have these properties, but for this example, I'm going to use star to represent the thing that's at the focus and planet to represent the thing that's orbiting. But again, anything in orbit has these properties. When we are close to the focus, the force on the 2 objects is at its greatest, which means the velocity of the thing doing the orbiting is also at its greatest. However, the velocity is always tangent to the curve, and the force is always the force of attraction, So it's not necessarily towards the center, but it's towards one of the focal points. So like right now, the force is not perfectly perpendicular to the velocity. So this force is causing a change in the velocity of the planet and causing a change in its direction. As we get further away, the force of attraction decreases, as does the velocity of the object. So in an elliptical orbit, the object's traveling the fastest when it's close and the slowest when it's furthest away. And the force of attraction is always changing. That's about all we can do when it comes to elliptical orbits right now. When you guys have a little more math under your belts, we're going to talk about more that has to do with elliptical orbits. And we will cover a little bit about transitional orbits, but that'll be tomorrow. What I really want to focus on, though, is what we have for this particular unit, what's within our capabilities. And that is recognizing that situation when our elliptical orbit has an eccentricity of 1, meaning when the eccentricity is 1, we have a circle. Two things happen. First, a semi-major and a semi-minor are the same, and the two foci overlap, and there's a single focus at the center. This means our planet is traveling in a circular orbit, and the distance between the planet and the star is never changing, because the planet and the star now are separated by their radius of curvature. Meaning in a circular orbit, we are dealing with uniform circular motion. So we should be able to apply the rules of uniform circular motion to an orbit. Now, I believe that's all I should have to say, and you should be able to do any problem related to an orbit now, recognizing that the net force that's acting on the object in orbit is going to be the force due to gravity. Which means if we have an object at the center, which we're for this moment calling the star, and an object orbiting, which is a planet, and they are separated by a distance, r, the radius of curvature, then we can use the force of gravity as the unbalanced force that is causing the planet to be in centripetal motion. I'm being very careful here about my use of nouns, and you probably aren't paying as close of attention as you should. In this example, we are choosing one of the objects to be at the center and one of the objects to be doing the orbiting. I am saying the star is at the center and the planet is doing the orbiting. By making that statement, you'll notice the planet is here, because that's the thing that we're saying is doing the orbiting. It's the thing in circular motion. That seems great when we're talking about a planet versus a star. But there's a bit of a gray area. When do we use center of mass? You see, one of the problems we have to contend with is that a star is much heavier than a planet. I mean, we saw it earlier today. Mass of the sun is times 10 to the 30th. Mass of the earth is times 10 to the 24th. The earth doesn't have much of a chance in causing changes in motion in the sun. But yesterday, you guys did the Earth-Moon system. In the Earth-Moon system, the Earth and Moon are of an appreciable size. So what's orbiting what? Is the Moon orbiting the Earth or the Earth orbiting the Moon? And the truth is, they're orbiting each other about their mutual center of mass. So the question is, when do we have to take the center of mass into account? And there's no hard rules here. Generally, you should always take the center of mass into account. But as a soft rule, I'll say, if the thing in the center is much greater than the thing that's orbiting, so much so so much so that the center of mass is inside one of the objects, you probably don't have to use the center of mass calculation. But if the center of mass is between the two objects, you probably do. All right.